Good afternoon, everyone. Thanks to my audience and to attending this talk. And then I'm glad to share my research, which is a collaborative effort at a Scala Software Group led by Cheryl Lee, who is sitting there, under the title of Application of Online Surrogate Models to Scientific Computation. So this is a very long title, so I'll explain each part of it. So first of all, we talk about the online surrogate models. The online modeling is different from the offline modelings, which in the classic context, we should have a data set. For example, we're doing the linear regressions, then we have a data set and we fit a straight line to it. That's the offline modeling where your data set once get and never change. But online modeling is a little bit different. That means that your data set could actually be accumulated sequentially, and you got the freedom to actually pick your next sequential samples one by one in each iterations. And then what do we mean by non-parametric? Okay, non-parametrics missing here is that the linear regression would fit a straight line to our data set. However, non-parametrically, you probably want to fit a curve to your data set to get a better fit of your model. And then you usually will have several choices, including smoothing splines and polynomial regression. And the Gaussian process regression is a more powerful non-parametric model that allows us to model the curve more flexibly, which comes also with the uncertainty quantification that we need. So I'm going to explain what I mean by the surrogate here. Surrogate refers to an approximation to unknown function. So our big problem is that actually we want to optimize a function whose analytic expression we don't know, so that we cannot use those regular optimization methods. For example, like the gradient-based methods, LBFGS, simplex method. Those are all ruled out because we don't know the analytic expression of the underlying function, and that's the reason why it is called a black box function. So what we're going to do here is that we're going to draw sequential observations. That means that I give you an input, and then a so-called black box function will give me an output. So our input is the y, and our output is the x. So if we look at here on the left-hand side, left-hand column here, we actually have three different samples, sample from the underlying curve, and then we fit a blue curve here. There's a shady area, which is the counter interval given by the Gaussian process regression. And then on the right-hand side here, we actually have the so-called acquisition function, which is based on the surrogate model we fit. And then we can see that there's only one mode here, which expressed our belief that the next sequential sample should be drawn here to maximize the exploration trade-off. And then after several iterations, you can see here, well, since our underlying function is very simple, it's just quadratic. After several iterations, after 10 iterations here, we already reached the actual minimum. And the acquisition function associated with the current surrogate is actually a flat line, means that there is no room to improve. This is the general models provided by our software framework GP-Tune. GP stands for Gaussian process, tune means tuning. So basically, you can use our framework to actually tune any kinds of black box function in your high-performance computation. A very simple example being that how are you going to block your big matrix to reach the peak performance of a two big matrix multiplication, and also including some of our previous talks, there are a lot of hyperparameters in your high performance or physical applications that we could also help you to tune. So the previous framework we explained are very suitable for like scalar output. For example, we got an x, got an y, and then we're staying with the fairy tale world of like a scalar regression. So the two methodology innovation we did with our collaborator in the past 2 years is that what if your output is no longer scalar, but say like we got a closed curve output or functional output, which is more often than not in the scientific computation. For example, here in the statistical shape analysis, we're actually observing shapes or the sample points that were sampled from the from the closed curve. The closed curve is a representative of the shape class. And then how are we going to model such a kind of output? We developed a periodic kernel to ensure the closeness of the output, as well as we introduced this multiple output kernel so that it allows us to even to conduct the statistical shape analysis when your points were sparse and noisy, which is actually deviating from the idealized assumption of the classical shape analysis. And then next, we're going to consider a physical simulator application where there is a cosmology simulator whose output could be considered as a functional. That, for example, here we show the spectral functions and represented in terms of the point sample from it. So if we actually observe the spectral function represented by this sequence of blue points, and from some kind of cosmology emulators, and we want to find the actual configuration of this simulator that allows us to regenerate such a curve, then our framework will actually do the following. That is that it tries several other configurations, and by maximizing a specially designed acquisition function, we can actually got the orange curve, which is pretty close to the blue curve. That means that by actually sequential testing and evaluation of the cosmology emulator, which gives us the functional output, we can actually figure out what kind of parameter configuration we have to supply to this cosmology simulator so that we can generate this orange curve that's very close to the original blue curve that we observe. These are the two methodological innovations that we did in the past 2 years. Now we're going to show you two concrete applications that we collaborated with other HPC teams. The first application is that with our framework, we're actually introducing this ensemble of surrogates. For example, previously we introduced the Gaussian process surrogate, which is a single surrogate. So you can imagine that when your simulator or HPC application run on different machines or architecture, you'll get slightly different but somehow correlated surrogate models. So with our framework, we support the aggregation and the aggregation of different model, and therefore you can create an ensemble of different but similar surrogate model to further improve the tuning performance. With this method, we actually improve the scalar path performance by 28%, and also the Nimrod performance by 66%. And this work has been published recently, and feel free to check the IPDPS website. On the right-hand side here is the flow chart that shows the architecture of our framework applying to the specific application, which we also supply a historical database that stores past performance data as well as the past fitted surrogate models that allows us to do more complicated ensembling. The next application is this tuning hyperparameter for the randomized linear algebra library. As many of our previous speaker has already introduced, with the larger and larger matrix, one method to handle the regular matrix operation is to actually introduce some randomizations. So introducing randomization is a blessing and a curse. The blessing is that we can actually achieve the matrix multiplication or matrix operations or matrix factorization in much shorter time. However, it also introduces a lot of hyperparameters, and then the operation performance will highly depend on these hyperparameters. Therefore, working with the Berkeley group, we actually introduced this kind of tuning framework into the random LA pack, which is the randomized version of the LA pack. And then we hope that using our method along with the history database, when you actually install the random LA pack to your machine, that we can achieve the auto tuning so that you get a peak performance of the randomized linear algebra library running on your machine without too much trouble. So as for future works, we're actually considering introducing heterogeneous Gaussian process modeling for handling a different for handling heterogeneous noise across different configurations. We're also considering tree process for less smooth modeling of the surrogate. Online model reduction is another direction. For example, we actually, with more and more data and more variables, you imagine that your surrogate model is growing larger and larger, just like those giant neural network models that we saw. So online model reduction means that is there a way that we can actually reduce the model but achieve roughly the same performance as the all good surrogates? And then the third direction is very relevant, which means that we already have some pre-existing analytic performance model from the numerical linear library, numerical linear algebra community. Therefore, we are trying to figure out a way to combine the strength of the analytic model and our surrogate models together so that we can learn more about the performance of the numerical linear library. And thank you. This is the QR code. You can scan it to actually try a little bit of our GPTune framework. And then I'll take questions. Thank you.
Thank you, Hengrui, for a great talk.
Yeah.
Any questions from the audience?
Yep.
So thanks for that talk. I think that there's an opportunity to combine multiple of these projects together, right? To suggest which are the new data to go collect in the next batch.
Sure.
What are your thoughts there?
So we are doing a lot of collaborations and definitely. So the next step, because the second efforts we're doing the functional output is still like ongoing process. So in this talk, we mainly focus on the non-standard type of outputs. So one direction I would say it is the non-standard type of input that actually posed an additional challenge to the kernel design of the underlying surrogate. And that in that way, we can actually imagine such a situation that actually your input is a tensor, but your output is a functional thing. That will be an additional challenge both to the surrogate modeling and also uncertain quantification, I would say. So uncertain quantification is something that we support, but we hope to do more work in the future as well.
Any other questions from the audience? Okay, if not, let's thank Hengrui once again for a very nice talk.
Thank you.